So the next speaker is Amos Fiat, and he's going to teach us how to bribe a prison guard.
Well, good afternoon. Actually, I need to learn how to use that mysterious... Okay, so I gave this talk, or a version of this talk, a while back at Google. Isai was in the audience. After the talk, he came up to me and said, don't mention this problem, it's irrelevant. I decided not to take his advice. But I'm giving this as a major motivating example, and also it fits well with what I'm going to describe, although what I'm describing is somewhat more general. So this is the problem that I'm sure many of you have spent sleepless nights thinking about. So there's M agents and tasks. The goal is to assign the tasks to the agents so that they're done as soon as possible. And agents lie all the time. And the problem that Norm and Amira suggested was finding an incentive-compatible or truthful mechanism with a good approximation for this problem. And this problem has been open for over a decade, and it has had all sorts of partial progress made, but it's still open. But there's all sorts of other solution concepts about. In fact, I know very little about the other solution concepts, but I've spent some time with Anna reading about them, and with Elias. And so there's other solution concepts like undominated strategies, iteratively undominated strategies, and so on. And there's big surveys with lots of pages about them. And they actually claim, they have statements like you can implement anything, any social choice function, anything basically. But these things are not completely relevant to this context. So they have all sorts of faults. In one setting, these AM mechanisms, they require common knowledge. And this is serious cheating in any mechanism we want to implement, because there's no common knowledge. It's not that everybody knows exactly what everybody else is doing, and you can bribe them to tell you about it. And there's all sorts of technical difficulties with this problem using other techniques. And there's lots of dirty tricks in these. I'm sorry. How do I get this? Green. Oh, here.
No, this one.
This one. Good. It's interesting reading, and they have interesting tricks that they use. Some of which could certainly be considered dirty tricks. Infinite sequences of undominated strategies, embedding the traveler's dilemma into the problem, and all sorts of other fun stuff. But they do get some notions of interesting implementation ideas, none of which can in any serious sense be considered a solution to the make-spam minimization problem. So this is the bragging slide. And I'll explain it, it's really bragging. So the mechanism for make-span that we're presenting is truthful and expectation. It's probably approximately correct. So this notion of probably approximately correct comes from, of course, from learning, but it sort of appears in mechanisms too. They have these virtual mechanisms which are approximate. So these ideas have been around in the context of mechanisms, but this mechanism is going to be probably approximately correct. So with high probability, a 1 plus epsilon approximation in the make-span, which is fairly good. And I'm fudging it. Okay, so I'll just give you the definition. So I looked up. Present or deal with something in a vague, non-committal, or inadequate way, especially so as to conceal the truth or mislead. Adjust or manipulate facts or figures so as to present a desired picture. I'll be using this thing in several places throughout the talk. And I can't explain in what way I'm fudging it. There are all sorts of missing details, but if you're really interested, we can go into them. Preferably not Now, there's a confluence of ideas here. So there's these virtual mechanisms which I didn't know anything about until very recently. And of course there's this notion of probable approximate correctness, which is in some sense like virtual mechanism. And there are these things called scoring rules, which we actually saw in a talk just 2 days ago, I mean in your talk. And these scoring rules are some way of encouraging best effort predictions. And these things are very strongly related to what I'll be talking about here. And it's not surprising, I'll explain why. There's this thing called responsive lotteries, which has just come up recently. This is Feigen and Tenenholtz. And essentially what they're doing is that they're noticing that you can set up a scoring rule. It's a lottery, and in some way what I'm talking about is very intimately connected to this idea of setting up a lottery. And then there's all these undominated strategies, iteratively undominated strategies, and so on, which are related. Truthfulness of expectation is related. I mentioned Silvio's papers. Now, there's another thing that's the same tricks have just been used. I've seen in another paper that was presented here, just not in this conference, but a few days ago, by Ron Smorodinsky. Is he here? Ron? No. Oh, yeah. Hello. So there's Maxerian Talwar said, let's use differential privacy so as to get something that is almost truthful. Almost truthful meaning that essentially it doesn't really matter what you do, so you might as well tell the truth. And then Ran and Mose and Kobe said, well, this actually is, let's fix it. And let's fix it by somehow giving a greater incentive to telling the truth. Because you don't care so much, let's just give you some incentive to actually tell the truth. And in some way, this is all in the same spirit of a lot of these ideas happening here. So there is a confluence of ideas here. And okay, so let's talk about truth. So how does truth arise anyway? So one possibility is that the informer tells the police or the mechanism, right? And of course, one possibility is that this is via common knowledge. I happen to know what you have in your briefcase. I mean, and so I tell the police, and that's fine. It's common knowledge. Oh, something indirectly, because I know something about, I'm telling you something about myself for whatever reason. I mean, somehow the mechanism somehow induces me to do so, and therefore you learn something about others, perhaps. But what happens if you're alone? I mean, how do you make somebody inform about herself? This is a rack for those who are unfamiliar with the device. You don't have that at home? You don't have that in the basement? No?
I'd love to use it, but not self-use. Here's racket.
Okay, so what is this? This is 2,300 years old, and it's in Rome, city of Rome, in a church. I'm sure many of you have seen it. It's an early form of polygraph. It punishes liars. It appears in the famous movie, Roman Holiday, Lily Peck and Audrey Hepburn. And you can see actually what happened here. See that his hand has been cut off? I mean, you put your thing into here, you tell a lie, and your hand gets cut off, so you get punished. This is a low probability event, by the way. Okay. So we really want to build something like this. This would be really useful if we could, have this thing just before we have a mechanism, and just before people come in, they have to put their hand in this thing, and they tell us what the type is, what they know about the world, whatever we want them. And if they lie, then they have a strong incentive here not to lie. I mean, maybe even more than winning a few dollars in an auction. Then this would be a good thing to build. And so you want to build one of these truth enforcing mechanisms. Okay, so we want to devise mechanisms that punish you for lying. And once we have this thing, we can we start up. I mean, this is an optimization problem. We want a mechanism that punishes you as much as possible. This actually will come into play. This will have part of. This will later actually have influence on what the final result of the mechanism would be. But think of it as an optimization problem. We want some mechanism that if you tell a lie, you'll get hit on the head strongly. Now, when you talk about punishment, when you talk about punishment, the question is a function of what? So somehow it has to do of the value, perhaps. It's not completely well defined. That's a function of the utility you want to associate with a social choice function. It has to be a function of something. And then, what type of lie? Is it an additive lie? Is it a multiplicative lie? Is there some bounded range involved? Is it an infinite range? So these questions have to be answered, and you can try to optimize for these different criteria. You set up a set of criteria. You say, what is the best thing I can do in this setting? I'll show you one of such optimization. And I'm fudging things all over, but okay. So this is the basic tool, and this is a formulation of goods. And I'm actually going to talk later about the formulation of tasks. And how long do I actually have? I have no idea. Makes two of us, I guess.
Like 11 minutes into the talk.
Oh, okay, thank you. Okay, so this is one stolen Greek. There's a Greco-Italian, there's a strong Greco-Italian influence in the audience and in this talk. So, Greco-Roman, I should say. Okay, there's one stolen Greek vase, there's one mafioso bidder. And the goal is to. I'm sorry?
They bid?
Wow. So our goal is to get a good estimate of the value of this vase, this beautiful thing, to the mafioso over here. There's no priors and no other assumptions. Okay. So let's consider the following solution. Let the bidder, the mafioso, make an offer, V tilde. And now we're going to give him this thing with probability P of V tilde. And P is going to have some properties. Actually, I can make P almost anything I want, but it's going to be strictly monotonic, increasing, strictly concave. With this probability, I'm going to give the mafioso the vase. Otherwise, I'm going to break it. This is my mechanism. Now, making the offer is kind of a red herring, because what will the mafioso choose? He'll try to maximize his utility. So he says, well, the vase is really worth V. There's some probability I'm going to get it, which is P of V tilde. I'm going to pay V tilde. So he's going to choose V tilde that maximizes his thing. When he doesn't have to do it, I can do it for him. Right? So it's a strictly dominant to reveal V. Right? And note that given P and V tilde, this is what I really want from P. I want it to be invertible. Given P and V tilde, I know what V is. I know if it has a unique maximum, I'll be able to compute what V was. I want to invert it and get V. So this is like a truth mechanism. It's all I have to. I don't care about anything else. I run this thing, and I've given you very few restrictions on P. All I want to do is be able to invert it. So, and it's a dominant strategy for this guy to tell me the true value because he's maximizing his utility, and that's it. He tells me something, V tilde. It tells me I doesn't have to tell me this filter. It tells me V. I do this computation for him, and now he tells me the truth. And this can be done in all sorts of ways, by the way. There's many ways to do this, and if you look at scoring rules, you see that they actually have different ways. But as I said, we want more than dominant strategy truthful. We're in the same setting. The mafioso may have external reasons to lie about the true value. Now, this doesn't make sense in the normal game theoretic sense, because it doesn't make any sense, because this is the game. But we're actually going to embed this in a bigger setting. And in this bigger setting, there might be reasons to lie, because maybe this will impact something else that happens, like the make span. Think of a make span as something in the background. So we want to make it highly painful to lie about the true value. And that's why we want this thing. Okay, so let's use this example of Nissan, Norman, and Amir. So the problem is there's all these tasks, And there's all these agents, tasks, and this is the true length of the task and the agents. And the agents start lying. I mean, they lie through their teeth. So agent 1 gives you some values for this row, and agent 2 gives you his values for this row, and so on. So this is basically nonsense. And this is basically the input that the mechanism gets. Standard setting. So we start with this thing which is lies all lies. And we're going to do the following thing. With some small probability alpha, we're going to take this thing and we're going to use one of these truth extracting devices. And we're actually going to go on every single entry in this matrix. And we're going to extract the truth for this entry. Now this is not the same setting as before. This is not a good, it's not a vase. This is a task. So what we're going to do is we're going to change the wording a bit. Rather than having this being a vase, it's going to be a task being sent to the mines. And rather, it's going to be bribing the god rather than paying the auctioneer. But it's the same notion. So, and if I can do this thing and make sure that nobody lies on any one of these jobs, then if I would probability 1 minus alpha, if this thing is sufficiently painful, if this branch of the tree is sufficiently painful, if lying here is sufficiently painful, then I'm going to get a good estimate for every one of these values, and I'm going to get a good estimate for the May span. And in fact, and this is one of the ways we're fudging here, but if initially the values are, say, taken from a discrete set, from a grid, we're going to try to increase the punishment here to be sufficiently painful so that they're not even going to move from one point on the grid to the next point on the grid, which means there'll actually be truthful expectation. However, I haven't quite told you how could I possibly get so much pain out of this thing here. And one of the tricks and one of the fudges here is that I'm going to actually repeat this many times, and I'm using the fact, I'm changing the model now. I'm saying if I can give the same task 7 times, it's going to be 7 times as painful. And therefore, I'm actually going to be playing the same game on the same task many, many times. And I'm going to increase the pain slowly until it becomes the dominant thing, so it doesn't make any sense to lie about anything. If, by the way, I don't have, if the initial values are not on a grid, on a non-discrete grid, then what we don't necessarily get something that's truthful in expectation, but we get something that's an implementation of undominated strategies. Because even if it's not truthful in expectation, you can only lie a very small amount. And therefore, what you really get is a good approximation of the make span in non-dominated strategies. So this is the expected punishment for lying more than 1%. Any again 100 times 100 worst possible make span, and we're not going to do anything. And rather than have this 1%, you can think about lying more than the distance between any 2 grid points. And fudging it again. Okay. So let's go back. Let's look at some specific P's. I sort of gave this P, and I said all I wanted was it would be strictly concave, and then it would be strictly truthful. There would be dominant strategy truthful. But now I'm really interested in getting this punishment up. So I want to get a good P's. And again, I'm doing this in the setting of tasks now. So this is the prisoner. We're back in the guard, in the bribing the guard scenario. And I'm being sent to work in the salt mines. And the guard wants to get a bribe. And he wants this bribe to be his lot. Well, if you're interested in getting he actually wants to know how much he's going to get it. So let's see this thing. So there's a true cost, which is A. The agent claims some A tilde as the cost of the task. The agent pays the bribe, which is some function of A tilde. It's the same thing we had before. And the guard assigns tasks to the agent with some probability depends on A tilde. This is the general setting. It's just, I've just translated everything into terms of tasks and bribes rather than vases and mafiosi. Okay. So now, let's note the following. Let's take any function Sx, which is positive, such that, and let's take this case, I'm assuming that the true value lies in this range between the lower bound L and the upper bound H. This is the true cost. We can do things without upper bounds. And now let's just take any S of x, such that the integral from L to H is less than or equal to 1, which means that it's bounded. And we're going to use the following mechanism. This will be the probability of assigning the task to the agent. It's the integral from A tilde to H of S of x dx. As I repeat, take any S of x that obeys this, any of S of x whatsoever, and pay this bribe, the integral from L to A tilde of x S of s dx. What is the cost when the truth is A and the agent, the inmate, says A tilde? Well, this is the cost. The true cost of going to the mines is A, and this is the probability he gets sent to the mines. And this is the bribe that he has to pay in this mechanism. So this is the cost to the agent of saying A tilde when the truth is A. And just by taking the derivative, you can see that it is, in fact, dominant strategy truthful. In this case, it should be obvious. It's dominant strategy truthful to have A tilde equal A. But that's not what we want. We want more than that. Actually, I'm going to give you an optimal truth extraction for additive lying. So I'm going to choose this S of x, 1 over h minus L. And then I just plug it into what we had before. This is the bribe that's being paid in advance, A tilde squared over 2h minus L. This is the probability, that's translating what we had before, that the agent gets assigned the task. The cost of saying A tilde when the truth is A is the cost of the task times the probability it's assigned plus the bribe. The punishment you get, this is what we care about. We care about how much you get punished by lying. The punishment you get for saying A tilde when the truth is A is the cost for saying A tilde when the truth is A minus the cost for saying A when the truth is A. That's how much you get punished. We can then normalize and move things up again if we want things to be around 0. But it doesn't really matter. And this is what we get. This is in fact the optimal solution we can get when we want one constant additive error. We want to maximize the punishment for constant additive error, and we get the following thing: the punishment for A to A tilde is A minus A tilde squared over 2h minus L. Now let's try to interpret this thing. Say A minus A tilde is a constant fraction of h minus L. Then what we have here is in fact, so in fact A minus A tilde, one of these, cancels out with h minus L. And what we have here is a punishment that's proportional to the lie. So if you lie by an additive x, and x is large compared with h minus L, with the range in which you're in, your punishment is going to be proportional to the lie. And this is actually optimal for this case. I think this is where I was planning to end. Our tooth went out. Thank you very much, and I'm happy to take any questions.
Any question?
Jokes? No.
Okay, then let's thank the speaker again.